Radioactivity is the nuclear radiation emitted spontaneously by an unstable radioactive isotope. Of the known isotopes of all the elements, there are 264 that are stable, and 300 are naturally occurring but are unstable. An even larger number of radioactive isotopes, which we call artificial isotopes, have been produced in the laboratory. Different forms of radiation are emitted when a radioactive nucleus is converted to a more stable nucleus. And so that's what radioactive isotopes do. They are unstable and they will spontaneously emit radiation to form a more stable nucleus. Now, the different forms of radiation can include these four following: the alpha particle, the beta particle, a positron, and a gamma ray. Let's take a look at each one of them. So an alpha particle has a symbol that's a helium nucleus. So it has a mass number of 4, an atomic number of 2, and the symbol He. It can also be written using the Greek lowercase alpha, but the helium notation is more easily used in a nuclear reaction. An alpha particle is relatively large compared to the other particles. It has a 2+ charge, it's very slow moving, and it can be stopped by paper. Alpha particles, when next to your organs, can do a lot of damage, but they really can't penetrate the skin. A beta particle is a much smaller particle. It has a symbol of a 0, -1, and an E. You could also use the symbol of the lowercase letter beta in the Greek alphabet, but the symbol with the E is more useful when writing nuclear reactions. The beta particle has a negative charge, and what I find very interesting is considered an electron from the nucleus. Now that might give you an exclamation mark, like, what? Electrons in the nucleus? But remember, what's happening is you have an unstable nucleus. And then in this nucleus, a neutron is converted to a proton. And in that process, it also makes a beta particle, which is similar to an electron, but it's emitted from the nucleus. Beta particles are smaller and move faster, so they have deeper penetrating power, and they have to be stopped by aluminum foil. The third particle, which I kind of consider a cousin to the beta particle, is the positron. It has a mass number of 0, and it has a +1 atomic number. It also has an E. You could use the Greek letter beta with a plus. The positron has a +1 charge, would have similar penetrating power to the beta particle, but this one is not as common. And the last of the radiations here is a gamma ray. Gamma ray is not a particle at all. This is very high energy electromagnetic radiation. Electromagnetic radiation would include things like ultraviolet light, infrared light, visible light, TV waves. So this is energy that travels through space as a wave. Because the gamma ray is not a particle, it does not have a mass number or an atomic number. You really could think of both of these numbers as being 0. So they just use the symbol for the Greek letter gamma. You can see here, as I mentioned, it's high energy radiation. It has a much greater penetrating power, so it has to be stopped by a piece of lead. Because it doesn't have a mass number or an atomic number, there is no transmutation. Or in other words, if only a gamma ray was emitted, then there would be no new nucleus formed. Sometimes the gamma ray is emitted in conjunction or along with one of the other particles. So when writing nuclear reactions, we have to consider how to balance them. And it's a little bit different, or a lot different, than a chemical reaction. So we have to first look at the mass number. The mass number is the number in the superscript. And what we know is that the sum of the mass numbers has to be equal on both sides of the equation. So let's take a look at the reaction below. So on the reactant side, the mass number here is 241. And what the above statement means is that must equal the sum of the mass numbers on the product side. So 4 plus 237. So this also equals 241. So that would be considered a balanced nuclear equation because both sides have equal mass numbers. Now we also have to consider the atomic numbers. And again, looking at the sum of the atomic numbers, they must be equal on both sides of the equation. So let's take a look at this equation here. So on the reactant side, we have 95 as the atomic number. And on this side, we have 2 plus 93. So 2 plus 93 is 95. So this equation that was written is a balanced nuclear equation. So let's take a look at the different types of emission of radiation and how we can write our own balanced nuclear equations. So an alpha emission. Now when trying to write a nuclear equation, it's most helpful to write the alpha symbol as the 4,2He. So this says write the balanced equation showing the decay of thorium-230. I'm going to write this a little lower. Which emits an alpha particle. So I know that I'm starting with thorium-230. 230 is the mass number. I have to find thorium on the periodic table. And looking at thorium on the periodic table, it is element number 90. So that's the atomic number. And it's producing an alpha particle, which we would write 4,2He. Well, looking at this equation, this is not balanced. And so what we know is that a new isotope also must form. And remember, in the process of a nuclear reaction, radiation is emitted so an unstable nucleus can form something more stable. So to determine what the new nucleus is, we look at our mass numbers first. So this side has 230. This has 4 plus some number that we would need to put right here. So 4 plus 226 would equal, then these numbers together equals 230. So I know the missing mass number must be 230. Now I would do the same thing with the atomic numbers. So in the bottom we have 90, and that must equal 2 plus the atomic number of my unknown isotope. And so I see 2 plus 88 would equal 90. So the atomic number of my new element that's formed must be 88. Now, in order to know what the new element is, you would need to get out your periodic table and look for element 88. And element 88 is radium. So this right here now is the balanced nuclear equation for the decay of the thorium-230 by emitting an alpha particle. So let's look at a beta emission. And so the symbol that's most helpful for beta is the 0 as the mass number, the -1, and the E. So I look at the problem, write a balanced nuclear equation for the beta emission of iodine 131. So I have 131, and I know iodine is the element. To figure out the mass number, I look on the periodic table, and I find that it's 53. Now the problem has told me that it emits a beta particle, so I put a 0, -1, E. Now I have to determine the new isotope or the new nuclei that is formed when this happens. So to do that, I first look at the mass numbers. So I have 131 equals, this is a 0, plus some known number here that's going to go for my new nuclei. So since it's added to 0, I would know that this has to be 131, because 131 plus 0 is 131, which is what I need it to equal. So I have 131. Now I will do the same thing with the atomic numbers. So down here I have 53. This atomic number is a -1, plus some number, which would be the atomic number of my new isotope. Now remembering that this is a -1, so this would have to be 54, because 54 plus a -1 would equal 53, making the two sides equal. To determine what element this is, I would, to determine, 54. I'm sorry. This is what I figured it out. And to determine what element it is, I would look up element 54, and that is xenon. So this right here, including all of it, is the balanced nuclear equation for the beta emission of iodine 131. Now we have a positron emission, and the symbol for a positron is a 0 as the mass number, a +1, and an E. So this says write the balanced equation for the positron emission, which I know the symbol for, of arsenic 74. So arsenic is As, and it tells me it has a mass number of 74. And then when I'm looking at the arsenic, I have on the periodic table, I see its element 33. So this says I have a positron emission, so I write my symbol for positron. And now I have to figure out what the new nucleus that is formed. So on this side, I have 74, and that has to equal 0 plus some unknown number here. Well, to make both sides equal, that unknown number must be a 74. Because 74 plus 0 would equal 74. And remember, in a balanced nuclear equation, the mass number on the reactant side and the product side have to be equal. So now I'll do a similar thing with the atomic numbers. So this one is 33, and that has to equal a +1 plus some number, x, right here. That number would be what this is. So it needs to be a 32, because 32 plus 1 is 33, and both sides would have to be equal. So I have a 33. Then to figure out what element it is, I look on the periodic table, and element 32, I'm sorry, 32. That's what I said here. I got distracted because I was saying that both sides are 33. So element 32 would be germanium. So now looking at the entire equation, this is the balanced nuclear equation for the positron emission of arsenic 74. Now gamma emission, which is just a gamma, it says write a nuclear equation for the decay of iridium 192 with both beta and gamma emission. So let's start with iridium, which is IR, and we have 192. And IR, if you find it on the periodic table, is element number 77. And this says I have a beta decay, which is a 0, -1e, and a gamma. So now to figure out what my new isotope would be, on the reactant side I have 192. That must equal 0 plus the gamma ray, which would also, if you want to consider it, would also be like having 2 zeros. So that's not going to change it, plus the number for my unknown. So this number would have to be 192. Because 192 plus 0 and 0 would give me 192. Now looking at the atomic numbers, this one is 77. I have a -1 plus, this would be like adding 0, plus whatever number would go down here. So 77, this would be plus a -1, so this would be a 78, because 78 plus 0 plus a -1, these all together equal 77. So the atomic number would be 78. And so then the symbol of that new isotope would be element 78, which is platinum. And so the balanced nuclear reaction for the decay of iridium 192 with both a beta and a gamma emission would be right there. Now I wanted to show you this example because if you see here we have a coefficient. Now what this coefficient means really is that I have 2 of these neutrons, so you could think of it separately like that. Or you could see that if I want to figure out what it's going to add to the mass number or the atomic number, I could say 2 times 1, that would be a 2, and 2 times 0, and that would be a 0. So adding it up, on this side I have 235 plus 1, which is 236. And that's going to equal some number I don't know because I have a question mark, plus 97 right here, plus the 2. So these two together are 99. So what plus 99 gives me 236? And that would be 137. All right, so my x, this number must equal 137, because 137 plus 99 equals 236. And now let's do the same thing with the atomic number. So this is 92 plus 0, so that's 92. And that has to equal some number that I don't know. So some number plus 42 plus, you see down here, 2 times 0, which is 0. So that would have to be, x would have to be 50, because 50 plus 42 is 92. And so then to figure out the element symbol, I look up element number 50, and I have 10. So the question mark would be 137, 50, SN. So let's try the next one. Now looking here, I see twice. Here I have a 2. So 2 times 1, that means this is 2 on the mass number. And 2 times 0 means it's going to be 0 on the bottom. Now we have 6. These are beta particles. But 6 times 0, that would be 0 on the top. And 6 times -1 is -6 on the bottom. So let's go ahead and try to work it out. So this has 235 plus 1, so that's 236. And that has to equal some number that we're trying to figure out, plus 140, right here, plus 2, plus, this would be 0. So this whole thing right here is 142. So I'm just thinking, okay, I have 236 on the reactant and 142. So let's see, that's 494 would be the difference. So this number would have to be 94. And then I would do the same with the bottom. So this is 92 plus 0, so that's 92. That equals some number I'm trying to figure out, plus 58, plus 0, plus a negative 6. So these numbers all together equal 52. So this number would have to be 40, because 40 plus 52 would equal 92. So this would be a 40. And to figure out what element it is, I would have to look up element 40, and I would see zirconium. So the answer for the question mark here would be 94, 40, zirconium. So you can see by knowing the symbols of the different types of radiation and by using the idea that a balanced nuclear equation, the sum of the mass numbers and the sum of the atomic numbers have to be equal on both sides, given enough information, we can discover some of the new or missing elements.